parent graph for each one. This is the way the parent, I'll leave it on the board, that's the way the parent graph looks for sine. And a couple of my students were concerned about Professor, you say it goes on forever, it does. And I can label more here if I wish. But let's continue, but all I'm looking for, if my students recognize that is a paragraph for sine. If you want to extend it on, go for it. Extend it to the left, go for it. But that's the way the parent graph looks. High, max is 1. Low, -1. And then, of course, you got things in between. By the way, guys, if I ask you what's the sine of pi, and you did not want to go to the unit circle to find it, now you got a graph. The sine of pi is right here, and this is the sine graph, it's 0. The graph is at 0. So sine of pi is 0. If I ask you what's the sine of 3 pi over 2, and you did not want to go to the unit circle and know what it is, sine, this is the sine graph, it's down at what? -1. So sine of 3 pi over 2 is just directly from the graph. Is -1. Without referring to that unit circle each time. Okay? So that's the way the parent graph looks. Now, is there a parent graph for the other 5? There are. Now though, before I jump into, I can't get all 5 done today, what do you think is going to happen with this parent graph that we've done in this class before? Except we didn't have a parent graph for a sine function. We had parent graphs. Transformations. Now, I know a 6-week course will drive you nuts. All of a sudden, you finally see the parent graph for sine, then all of a sudden they ask you, now please sketch this. Hang on, let's call it part B. Let's call it Y, F of X. Now, it looks like this. Therefore, you go to this graph, which is the parent graph, and do what to it? What's that 3 out front tell you to do as far as the transformation? Vertically stretch it by a factor of 3. And I can do that easily since I got the parent now, like next to me here. Let me erase this, under space. Put a black marker here, guys. I said multiply the y coordinates by 0. So it's 3 times 0 is 0. That stays right where it is. Let's hope this holds up. When I get up to my high point at 1, I got to multiply it by 3 to stretch it. So now it goes up to 3. It's up here. 3 times 0 for pi, stays right 0. 3 pi over 2 is down at -1. Multiply that -1 by 3, you're down at -3. No problem. You're down here. And of course, when you finally reach the end, 2 pi is at 0. 3 times 0, though, no effect. Stays at 0. Now your graph looks something like this. Same shape, except it's been stretched. That's all we're doing, a vertical stretch, but you have to know the parent graph. Now, here's the issue coming up, and I'll take questions. That was done. And by the way, guys, the range on this one, especially the range on that black graph, the up and down, that extends from a -3 up to a +3 for the range on this graph. And it continues forever, just like the parent did, so forth and so on. And then, hang on. Letter C, Mona, I'll take the question in just a second. If you saw this, now hang on guys, I don't want to scare you. Good luck. We'll just jump right into it. I'm still on sine. You haven't seen cosine yet, or tangent or secant. Now, Mona, what was that question?
If we're vertically stretching it, and so then there are points where y is greater than 1 or -1, greater or less than, then doesn't that contradict the unit circle?
Oh, beautiful. We're not on the unit circle right now. Where they say multiply this by 3. Where is it? Right here. Oh, this right here. You multiply the parent graph by 3, you're off that unit circle. So you're going back to the unit circle and showing me a vertical stretch on the unit circle. So it's actually being stretched. Okay, multiplying by 3 here. Oh, I know exactly what you're thinking. Guys, look at this one. Now, I don't know. I'm looking at all the colors I have, and you know how patient I've been in transformations, I'll grab the parent graph, I'll do the next one, I'll do the next one, I'll do the next one. Baroque, it takes forever to do all this. So I've got little schemes here, tricks to get to the final graph without going through all those transformations. But I want to point this one out. Can anyone remind me what on earth would this mean to do if I were going to use this color in terms of a transformation?
Flip it about the x-axis.
Reflect through the x-axis. You say, oh no, Professor, we're back to this. We are. Reflect through x-axis.
Quick refresher, does that negative sign affect the theta minus two?
Which one are you looking at?
Like that negative sign out front?
No.
Okay.
Okay. And then if I should do it in blue next, I see a 2. Well, we saw what happened with the 3, so this is a vertical stretch, not shift, by 2. If I were to do it in blue. Now I'm inside, theta subtract pi over 2, they may want you to do what there?
Horizontal shift.
Horizontal
right,
shift.
Pi over 2.
There you go, horizontal shift to the right. Pi over 2. Same transformation we always work with. And as if that's not enough, we got plus 4, which might indicate here to do,
Vertical shift up.
yeah, vertical shift now, up 4 to finish this thing up. Up 4. Woo! Hey guys, please. Please. You're supposed to place the parent graph. That orange graph. Supposed to place it first. And then do this to it, do that to it, vertically stretch by 2, shift to the right, vertical shift up, and then you finally get your result. On that crazy curve over there. Did I identify with Eric's help? Did I identify the transformations correctly? Now, this is the only one I'm gonna do about transformations. And I've been messing myself. Because they get messy. Real messy. And I'm trying to use different colors to help myself out and they still get real messy. So you'll see a little shortcut pretty soon. Okay, Leo, Eric?
Could a more, like, when you have these really messy transformations, especially with numbers like pi and sine, would a more accurate way of doing this not to be to find the critical points and then use the transformations to change those critical points?
I'm gonna show you something that may help us a little bit later, which may be what you're talking about.
Because of the vertical shift up 4, does that change our horizontal asymptote up 4?
No,
Oh.
change your what?
Horizontal?
Oh, the horizontal asymptote, beautiful. The horizontal shift, you mean?
Yes.
I don't have a horizontal asymptote. By the way, guys, does this thing have asymptotes?
No.
Thank goodness, no.
It has range restrictions.
Yeah, it's got range, but does it, do you see a vertical or a horizontal asymptote on this thing? So that's one, thank goodness, that is one thing you don't have to worry about. Okay, I'm gonna graph this. Darn it, Park, I forgot to ask you to go over and get my straight edge for me.
Oh.
Don't you do that, cause I may, yeah, who knows, come on. You know where it is, right?
Yes.
Make sure you lock my door back. Okay, guys, we'll try to do this best we can. Bear with me. Okay. I guess I got orange, blue, green, black, and I need the parent graph. Hang on, let's get the, oh, red. Let's put the parent graph, guys, this parent graph in red here. So it's 0, pi over 2, pi always on this parent graph, 3 pi over 2, 2 pi. We know it goes up to 1, max, down to a -1, trying to make it reasonable. You guys just draw the parent graph for me, you get partial credit, it's just like that. So sine of 0, we know that, what's here, pi over 2 is up here for sine, 0, 3 pi over 2, 2 pi. Quick shape, something like that. Now that in the red is parent, just like over here. If you want to label it, y is equal to sine x. Is that true, guys? That's my parent graph. Do we accept that? Okay. Now, the one in orange, you guys told me, now reflect that through the x-axis. Good luck. Here we go. Reflect it through the x-axis, flip it over the x-axis. This point stays where it is. This point goes down here. This point stays on the x-axis. This point goes up to here, and this point's going to stay right where it is. This is orange. Flip over, connected. It might look something like that. Would you guys agree with that? Is that a reflection of the red into the orange? And the orange represents this. Okay, now on the vertical stretch by 2, looks like I'm going to do that in blue. Now I'm supposed to vertically stretch this by 2. The orange graph. Just multiply the y coordinates by 2. Talk about badness. I'm going to get ready for it. We'll go up to 2, drop down to a -2. Just get ready for it. The guys are on top of the board. Help me out. This is being done in blue. Right here, 2 times 0, that's what it comes down to. It's going nowhere. Here at 1, 2 times 1 is 2. Please, does it make sense it should go up there? I'm doing the orange graph. I should be messing myself. This is -1. Oh, yeah, this is -1, right? So it should be where? -2. Please help me out. We got 0 there, we got that. That's that one right there. Here's 0 again, 2 times 0, stays right where it is. I'm looking at the orange graph. Finally out here, it's up at 1, now it's up at 2 on the orange, and then back to 0. Is that making sense? Went through and multiplied the y coordinates by 2. If I do, Jonathan's going to look something, if I have no mistake, and then on top of the board, it's very easy to make a mistake. Is that reasonable to show in the blue a vertical stretch by 2? Does it look like maybe the orange graph has been stretched by 2? Woo! Anna? You can see all this in Math 8, and they ask you to take a derivative of it, or do some calculus on it. Oh my goodness. Here we go. Now the green. Let me mess up myself here. Now I'm supposed to horizontally shift that graph, blue graph, to the right, pi over 2. It's getting messy. Shift the blue graph, pi over 2 to the right. Oh my goodness, help me out here, help me out here. Okay, if I start at 0 and I shift it over pi over 2 to the right, it's going to start here, I guess. And where should I plot the point? What was my blue graph? Was it down here? Okay, so it's going to stay here. True? Is that it? Shifted over to the right? Yes? No?
No, because isn't that one the 0?
Okay, 0 right here. That's on blue. If I shift over pi over 2 to the right, is it now here?
Yeah.
So you're telling me the green is right here. Here you go. Keep track of it for me. Help me out. Now I'm at pi over 2. You're going to shift another pi over 2. Is that true?
Yeah.
Pi, and what should be happening to pi? Should be down here? Help me.
Yeah.
It was down there and now it's been shifted over. Yes, no? And now I'm at, where am I? I'm losing myself.
You're up on that.
Pi now, and add another pi over 2. You're adding pi over 2 to the right. Woo! That's going to take me up to what? 3 pi over 2. At 3 pi over 2, now over here, it should be doing this, which was here. Yes, no?
Yeah.
Whoa, all right. 3 pi over 2, Jonathan. Another pi over 2 will take me over to 4 pi over 2, which is 2 pi. Takes me over 2 pi, and what should be happening there at 2 pi.
It's up to,
Is it up here? Is that true, guys? Woo! Now, hang on, I'm gonna connect those in the green. It looks like if I connect them from left to right, if we have no mistake, and my students have helped me out here. It looks like that, if you guys can see the green, it looks something like that. Look at the time it's taking. Up to here. I want one more item. At 2 pi, 2 pi, I think we're right here, weren't we? I need to add also pi over 2 to it, which now is going to extend me out to, what is 2 pi plus pi over 2? Put together the common denominator of 2, where am I? 5 pi over 2 is what I want here. So now that 5 pi over 2 is extended, and what should be happening at, for the green, 5 pi over 2, am I back on the axis? So that green graph is going to go back down to that. Now that looks like a better graph, like a wave. They call it sine wave. Is that true? You see the green? And the green is here, we're done. Oh, this one's too bad. Now the black says, please don't stop there. Vertically shift that green graph up 4, and then you'll be finished. Anyone tell me what does that mean for me to do to vertically shift that green graph up 4? Leo, go for it. What would you do?
For all y coordinates.
Add 4 to all the y coordinates on the green graph. Okay, where am I? Here's my start of the green graph, which is 0. So if I add 4, does that tell me with his help, am I now going to be, where guys? I'm getting ready for this. -3, in case I need this. Okay, I'm here. It says add 4 to the y coordinate. And what is the y coordinate here? 0, so you're going to add that 4 to it. So does that take me up to here? Yes or no?
yeah.
Woo. Now the green graph, my next point is down here at -2. Interesting. You're going to add 4 to that, which now takes me up to 2. And we're on Earth. Am I up here, guys?
Yeah.
Don't you mess up now, because I'm almost finished with this. Green graph is 0 here. Add 4 to it, and my back up here. Yes or no, guys?
Yeah.
Ooh. And green graph here at 2. I'm adding 4. Where am I there?
6.
Am I 6? Interesting. Jonathan, don't let me mess up here. Is that true? And finally, at this point on the green graph, I'm at 0, which says add 4, and I'm back at 4. This is the green one, we're back up here. Final graph. It's going to look something like this. Oh my goodness. Guys, all those colors, can you see the green graph? Does it look like with that black graph, does it look like the black graph has this shift up, vertically shift up of the green? And finally ends up with there. Now, Mana, all that effort, this black graph is a picture of all of this. It took me little pieces of transformation to get there. That black graph is the graph of the final function. Now let's list the domain and the range on the black graph if we can. Would you expect that black graph to continue if I wish to extend it on the left, right? Does it, you think it extends just like the parent did? I could add more to it if I wish. I don't want to because I have one cycle. They call it a cycle. I get one cycle, I'm happy. But the domain, the entire domain on the function here would be all real numbers. Right like that. I'm right like this. Now, be careful, guys. What's my range on my function? positive 2 up to 6. On the black graph, which means that's the domain of the range on the green function. This green function has a domain, negative infinity to positive infinity, has a range from, we said what, from 2 up to 6. That true, guys? Woo! Now, with all that said, I need some more vocabulary. Let me go back to my paragraph. Leo, on my original signed parent graph, the orange graph back here, we said if you wish, you could, when the cycle stopped at 2 pi, you could do this and draw another cycle if you wish. I think we agreed on that. And could I pick up with where the black leaves off and draw another cycle if I wish? So it goes on forever. Here's some vocabulary. First, let's get the amplitude, they call it. Just the amplitude, and here's what it is. The amplitude of the graph is the highest point from the axis that parent orange graph goes up to. So my parent graph is the orange. What's the highest point it goes up to? 1. So that's, it's said to be the amplitude of sine. That's the max from the axis. This one might have an amplitude of, let me go back to here, maybe a 2, because that's stretching. We'll look at that a little bit later. Something else, the period of the graph. We're saying, yes, we talked about this, that it couldn't repeat here, and we said, at what number would it start repeating if I wish? 2 pi. So I can draw another cycle if I wish. So the period of the graph is 2 pi. So every 2 pi, you get a cycle. Every 2 pi, you get another cycle. So, Jonathan, that tells me if I want to draw another cycle like this, from the extension of the orange, tell me where would this thing end? What would I call this ending point? 4 pi. Thank you. 4 pi. Add another 2 pi, about 6 pi, you'll get another complete cycle. So every 2 pi, this thing repeats. So we've got period, we've got vocabulary, not vocabulary, period, amplitude, domain, range on these graphs. And how many graphs have I done so far? 1. Sine. And I'm watching my time carefully. Yeah.
For the transformed graph, why would it be amplitude of 2 and not 6?
Beautiful, beautiful. Now, here's the question. You're saying, Professor, you are telling me this graph up here represents this function. True, guys? Here we go. Beautiful question. Let's see if someone can answer this for me. When I start shifting up, guys, what is I vertically shifting up for? Now, if I should go back to where I was, you know this is the x-axis. If I shift the x-axis up, it's not a horizontal asymptote, but if I also shift the x-axis up to here, can that now be thought of as the x-axis of my new graph? Is that true? How high up from there did it go? It went up to 6. How many units is that? From 4 to 2. That's why this works out to be a 2 if they should ask you what is the amplitude. It's measured from its axis. Mike, that's what you had questions. Okay. The period of this final graph, let's get the period out of the way. We know the amplitude is 2, which is usually this number right here stuck in front, positive always. That will give you the amplitude. The period of the graph, I said, well, Professor, I saw back here you said on the parent graph, at 2 pi, if I pick up, I could draw another cycle. Does anyone have an idea where could I start drawing another cycle? I want to start drawing another cycle right here. Right? And then we tell you the period, or I can find out the period. Guys, let me think now. Hang on, I gotta be careful with this myself. Whew. Real careful. Does anyone have an idea of what the period number might be? It was 2 pi over there. What might it be on the black graph? I see where it ends. It ends right here. At, where was it? Yep, yeah, I got it. Was that 5 pi over 2?
Is it 5 pi over 2?
That's where it stopped. Where did it start?
Prior to.
How much distance, this is another way to think about period, how much distance was covered from pi over two to phi pi over two?
Prior over two.
Well, if you subtract those two, find that distance. Okay, so the period could be followed as 5 pi over 2, that's where it stopped. Subtract where it's, where it started at pi over 2. 4 pi over 2, better expressed as 2 pi. So it has a period of 2 pi, just like its parent did.
What transformation would you make to change the period? Would it be a stretch?
Beautiful.
Would you put it as
Beautiful, that's why I love this.
It'd be a horizontal stretch, right?
Right here.
So it'd be 1 over 3 thing or something like that?
You said, Professor, how can I change the period? It's 2 pi, just like the parent was on yours. If it looked like this, guys, we're gonna do it today. Eric, beautiful question.
That would shrink the period.
That's what shrink the graph and change the period. Okay, the shift did not. Okay, so that's coming up later on. We brought that up. Guys, make a little sense here? It takes a little effort. Now, with my time here, you said, Professor, hang on. You're telling me there's a graph that I'm responsible for, Jonathan, you're saying for all 6. They all have graphs, Professor. You've done only one. I'm gonna try to get 2 more done and nothing more to do with them. I'm not going to do any transformations on the other 2. I'm gonna go ahead and show you what the other parent graphs look like, and I'll give you all 6 and what they look like. I think the next one I'm gonna pick up is for a reason, and you're going to tell me what the reason is. Part C, I like to sketch. Just to see what the parent looks like for this. F of x is equal to cosecant x. Get ready. Get ready. Now, with that said, anyone tell me why of the 5 remaining ones with range to choose? I thought, Professor, you would grab cosine next. Why would you jump and do cosecant today?
You want to show us that they're undefined at certain points?
Oh, beautiful, I love that too, something else.
It's the inverse of sine.
No, something else. Whoa, tell me again.
Inverse of sine.
Okay, it's the reciprocal of
Reciprocal of sine.
sine. So if I want to graph cosecant, Leo was going to wait, Professor, I know cosecant is this. There's a relationship with it and that. The relationship, they are reciprocals. So I'm gonna try to do reciprocals. Okay, now what I'm gonna do here is, here goes. I'm gonna first, I want you to get a paragraph today, guys, bear with me. I'm gonna first do this. I'm gonna redraw the parent graph for sine. 0. I've seen this so often, you'll pretty soon have to memorize. These are my critical numbers. Eric, I heard you say something also that's important here. We have 1 down to a -1. And guys, we'll graph it quickly. The sine graph, this is the basic sine graph from over there. Start at 0, goes up to 1, back to 0 at pi, down to a -1, back to 0. And it looks something like this. Now draw to scale, relay work, this represents your parent graph. Why is it sign it? That's the graph over there. Now what relationship does it have for cosecant? Now why would I want to graph cosecant now? And you guys said they are reciprocals. Okay, here goes. Listen carefully. Let me get the easy ones out of the way first. I'm trying green here. I'm graphing cosecant now. Is my sine graph at pi over 2, is it up at 1? Right there's pi over 2, is my graph up at 1? What's the reciprocal of 1?
1.
1. If you want to think of 1 as 1 over 1, flip it over, that's when you do a reciprocal, you still get 1. So I know for sure this point's supposed to stay right where it is. On my cosecant graph. That's what I'm looking for. Another obvious one, I think, is this one right here. At 3, 5, or 2, it's down at -1. If you wanna think of -1 is -1 over 1, flip it over, form its reciprocal, what's that? -1 again. This point stays right where it is for my cosecant graph.
With the same x coordinate?
Hang on now. Same x coordinate. I'm going to sine, which is y. It's 1 over y, 1 over y. Guys, at 0, now help me out here. I know it's 0, 0. The y coordinate is 0. That's what sine is. What's the reciprocal of 0? There's a hesitation.
It's undefined. It's 1
It's
over 0.
undefined. The best you do is think of 0 as what? 0 over 1? That's 0. Flip it over, what
So
happens?
there's a vertical
You get
asymptote
1 over
y is
0.
equal to 0.
Is that undefined? Undefined. There is no reciprocal of 0 in mathematics. And to show that, I heard Eric say, Professor, you gotta show that's undefined by placing something we've seen before, a vertical asymptote at 0, like this.
So what x is equal to?
I'll put it in orange, guys. I know my graph's gonna be in green. That's a vertical asymptote. Now, let's jump out to, I got pi over 2, we got that one finished. That was pi. Here's my graph for sine at 0 on the x-axis, at pi. Is this what, guys? At 0? And what's the reciprocal of 0 again? There is none. So what's gonna happen at pi?
It'll be another.
Another asymptote. And finally, 2 pi, we do the thinking that we're doing right now. Yes.
So there's a vertical asymptote of
Yeah.
a period of pi.
Well, we're gonna talk about that, hang on. Those are my vertical asymptotes. Now, looking for the green graph. Plus, I've got a couple of points in green also to help me. And I've got those asymptotes. Does anyone, you know what a vertical asymptote, you can't touch it. Does anyone have an idea what the cosecant graph starting out might look like in this interval? And you got to pick that point.